In this video, I'm going to continue question number 17, problems 2.3 from elementary number theory by Burton. Prove that the expression 3n factorial by 3 factorial to the power n is an integer for all n greater than or equal to 0. Solution. Here we are going to use mathematical induction in order to prove that the given expression is an integer. First, we check for n equal to 1. When n is equal to 1, this expression 3n factorial by 3 factorial to the power n becomes 3 into 1 is 3, so we have 3 factorial. 3 factorial to the power 1. It is equal to 1. And we know that 1 is an integer. So we have seen that the result is true for n equal to 1. Now we assume that this given expression is an integer when n is equal to k. Now, when n is equal to k, the given expression becomes 3k factorial by 3 factorial to the power k. Suppose this is an integer. Let's say that the integer is m. Now we shall prove that the result is also true when n is equal to k plus 1. When n is equal to k plus 1, the given expression becomes k plus 1 factorial 3 factorial to the power k plus 1. Here we have 3k plus 3 factorial. In the denominator we have 3 factorial to the power k into 3 factorial, okay? And here we have 3k plus 3 factorial means 3k plus 3 into 3k plus 2 into 3k plus 1 into 3k factorial divided by 3 factorial into 3 factorial to the power k. Okay, now have a look here. Here we have assumed that this one is an integer and that is m. So see, 3k factorial by 3 factorial to the power k is an integer that is m. So now we have, from here we have 3 and inside we have k plus 1. 3k plus 2, 3k plus 1 divided by 3 factorial means 3 into 2 into 1. And in place of 3k factorial by 3 factorial to the power k, we put m, which is an integer, okay? Now these two get cancelled. And here we have k plus 1 into 3k plus 2 into 3k plus 1 divided by 2 into an integer m. Now see here, we don't know whether this one is an integer or not. And in the denominator we have an even number 2. So see, if one of these is even, then clearly we can say that this whole expression is an integer. So now we have to check when k is both odd and even. Now see, when k is odd, then what happened? When k is odd, this term would be even. Okay, and even is divisible by 2. So this would become an integer. Okay, and now when k is even, then which term would be even? This one. This one would be even. Then this would be divisible by 2 since it is even. Then this whole expression would be an integer. So clearly when k is odd and even, we see that this whole expression here is an integer. So by mathematical induction, what can we conclude? we conclude that this given expression is an integer for all n greater than or equal to 0.